Okay, guys, welcome to Physics 203, Class 23. This is actually the beginning of our unit on special relativity. And before we get into Einstein's theoretical ideas, which is probably what most of you associate with special relativity, we're going to take a look at the experimental situation in the 19th century regarding light and something called the ether, and an important experiment called the Michelson-Morley experiment, which set the stage for Einstein's theoretical work at the beginning of the 20th century. So the first thing we need to think about is the need for a medium for light to propagate in. So what do I mean by a medium? Well, first of all, in the 19th century, light was through Young's double slit experiment, interference experiment, which we've talked about earlier this semester. It was demonstrated that light was made up of waves, and then later in the 1860s, in 1865, Maxwell, as we also mentioned, came up with the picture of light as electric and magnetic fields waving through space. So the 19th century saw the rise of the wave theory of light. But the question is, with waves, so think about sound waves. Sound waves, as represented here by their amplitude and then the compressions of air and rarefactions of air, they propagate in air or in other gases or in water and solids, but mainly in air. And ocean waves have water as a medium to propagate in. So by a medium, we mean some background material or substance that the waves are carried along through, and they displace elements in the medium without those elements moving along with the wave. So the wave is a collective disturbance that moves along. So the question is, what medium, analogous to air for sound and water for ocean waves, would light and electric and magnetic fields be propagating in? And this medium would have to have some pretty interesting properties because it would have to be very light, because light can travel basically anywhere through any path. And yet, so this medium for light would have to be present through all of space, and things are moving through space. So, and they move in outer space. Planets seem to move without much friction. So this medium for light would have to be very have a very low density, but at the same time, it would have to be somehow very stiff, because the stiffer the medium is, the faster the waves propagate in it. So, for example, sound waves propagate faster through solids than they do through air, because solids are stiffer. They resist compression more. So, since light travels so fast, the medium it propagates in would have to be somehow very stiff to support these very fast traveling waves. So nevertheless, despite the fact that there's a lot of requirements on this medium, it was called the ether, as in ethereal. And in the 1880s, it was widely believed by scientists to exist. So, okay. So how can we try to detect whether this ether actually exists? Well, we can try to use velocity addition and attempt to see velocity addition with light, okay? And so how this works, I'll just remind you of relative velocity. So here we have a little guy on a cart or a truck moving at 40 miles per hour. That's our frame of reference A. And then we have a ball moving at 15 miles per hour relative to the ground. and then we have another person over here moving in the opposite direction, person C, at 60 miles per hour. So classical additions of velocity followed the law that the velocity of the ball with respect to A is just the velocity of the ball with respect to the ground, VB, minus the velocity of A with respect to the ground. So what does that mean? So velocities in different reference frames can be found classically by just adding, or in this case, subtracting their velocities. So for example, VBA would be 15 miles per hour minus 40 miles per hour, or minus 25 miles per hour. And that makes sense because this guy in A is going fast to the right while the B is going not as fast to the right. So from the point of view of this guy, let's say on a truck, this ball would actually be going backwards by 25 miles per hour. That's where the minus 25 miles per hour comes from. And another example, here, person C in say another car or truck is moving at 60 miles an hour toward the ball. So the velocity of the ball with respect to that person would be VB minus VC. Again, VB minus VC, but it'd be 15 miles per hour minus, and then since this velocity is to the left, it'd be minus 60 miles per hour, or 75 miles per hour. That also makes sense because since this person is moving toward the ball, it will seem to be coming faster. So that's the classical addition of velocities. And so the idea is that we'd like to do that with light. We'd like to see if light in its own medium, the ether, if a body is moving with respect to the ether, if light changes its velocity because it's moving with respect to the rest frame of the light in the ether. But since light has such a large velocity, 3 times 10 to the 8 meters per second, we would need something really high velocity to see any effect on the light through this addition. Otherwise, like 15 miles per hour wouldn't make a dent in 3 times 10 meters per second. So a good candidate, which was discovered, is the Earth traveling around the sun. The Earth travels around the sun at about 3 times 10 to the 4 meters per second, or 30,000 meters per second. And that's about 10 to the minus 4, so 1/10,000th the speed of light, which is fairly small compared to the speed of light, but it's large enough that with sensitive equipment, we might be able to, in principle, detect the effects of the velocity addition involving light and the ether. So how could we do this? Well, a guy named Albert Michelson, and a very important early American experimentalist, built something called an interferometer. Okay, so an interferometer basically has a light source which comes out and hits a partially silvered mirror. So some of the light goes through and bounces off mirror 1, bounces back and comes to an eyepiece, while some of the other light goes up to mirror 2 and comes back down a distance L2 and comes to the eyepiece. So these two separate parts, when they come back and combine together, they interfere. And when the beams are rejoined, they form an interference pattern of fringes, which is pictured here. Okay, so this is like something like in Young's double slit experiment. So the light from this path and from this path are interfering with each other because they take slightly different distances in going to different locations in the interference pattern. So it turns out that you can do a calculation. So there's an ether drift assumed here. So we're assuming that this interferometer is attached to the Earth, and that the Earth is moving with respect to the ether to the right with velocity v. Okay, so when light is moving to the right, it would actually be moving since the Earth, it's moving with the Earth, light would be moving with velocity v plus c, since the Earth would add a velocity relative to the ether to the light. And when the light is moving back, it'd be moving against the Earth's motion in the ether, and it would be moving with a velocity v minus c. Okay, so we'll actually do this exercise in class, but it turns out if you figure out the time to travel parallel to bounce from A to C back to A, it turns out to be twice this length over the speed of light times this factor 1 minus v squared over c squared. Okay, and you can verify that for v equals 0. So if the Earth is at rest relative to the ether, this drops out to 0, and we just get 2L1 over c, which would just be this total length divided by c, which makes sense. And then for the other direction, which would be perpendicular to the ether drift, remember the ether drift is to the right. For this direction, perpendicular, it turns out it's possible to show that it's a similar expression for the time to go up to the mirror and back, a distance L2 or twice L2. It's 2L2 over c times 1 over the square root of 1 minus v squared over c squared. So, okay, so we've got these values, and subtracting these two travel times, because we're interested in the difference in travel times of the parallel and perpendicular beams to figure out what happens with the interference, we just get this. This is just taking the two expressions from the last page and taking out a common factor of 2 over c. And then the clever and effective experimental design was to actually, the idea is to rotate the apparatus, so spin it around 90 degrees to the right, so that now the, whereas L2 was perpendicular to the ether drift, now L2 is parallel to the ether drift, and L1, which was parallel, is now perpendicular. So they reversed roles. So we can say delta t prime, the difference in times for these two beams to reach here, is the same expression here, but with L2 and L1 reversed. Okay, and so so in doing this rotation, we see that there's going to be a change in the relative times or the time differences of the two beams to reach the eyepiece. Okay, so we take the change in the travel time differences. Okay, so we take the change in the travel time from with the device oriented in its original position, rotate it, and look at how the time change is adjusted. And when it's adjusted, it changes from delta t to delta t prime, which would be different numbers. That leads to a shift in the fringe pattern, because a change in time between the two beams means they reach this point at different phase shift, and so it shifts the fringe pattern. Okay, and delta t prime minus delta t can be shown. This is just algebra. So if you subtract delta t minus delta t prime, you'll find that you get this expression here. I'm not worried about all the algebraic details here, and that this expression here can be approximated. It's kind of a bit unwieldy, but we can do approximation since v of the Earth, it would be so much less than c. This v squared over c squared is a really small quantity, and we can do something called the binomial approximation to simplify this whole expression. And if you're interested in that, check out equation 2.5 and appendix 3 in the text. But this is approximately equal to then v squared times L1 plus L2 over c cubed. Okay, so we can see it makes sense that the relative uh, time difference in shifting the apparatus is proportional to the square of how fast the Earth is moving through the ether, and it's also proportional to how long these beam paths are. Okay, so predictions and results. So here I've just reproduced this expression here. This is the prediction here. So Michelson used his interferometer first in Germany in 1881. He went to Europe to hobnob with scientists there. He had L1 equal L and L2 about 1.1 meter. And if you plug in the velocity of the Earth that I gave earlier, 3 times 10 to the 4th meters per second, the velocity of C, and L1 and L2 is 1.1 meter, that gives a prediction of delta t minus delta t prime equals 8 times 10 to the minus 17. Okay, sorry, this should be seconds, not centimeters. And a fringe shift fraction, it turns out, of about 0.04 fringes. So in that fringe pattern, the fringes should shift by about 0.04, which is very sensitive, but Michelson thought he could observe it. But in doing the experiment, he didn't detect that expected fringe shift, or indeed any fringe shift at all. Okay, so he was puzzled by this because he thought that the ether would, if the ether was there, we would have to see this fringe shift. So he went back to the drawing board and he paired with a guy named Alfred Morley. He went back to America. In 1887, later, 6 years later in Cleveland, he built a much bigger apparatus with effective beam paths of about 11 meters, so 10 times as big, and a more stable optical table to reduce noise that rotated on a mercury bath. Okay, so this was stone on a mercury bath for very stable. And since the L1 and L2 are 10 times as big, that leads to delta t minus delta t prime is 8 times 10 to the minus 16. Again, this is supposed to be seconds. And a fringe shift 10 times as big of 0.4 fringes. And that should definitely be observable. That would be like half a fringe. So despite trying the experiment, though, at different times of year, so for different times of year, because perhaps the Earth at a certain time of year is lined up just so that it has zero velocity with respect to the ether. But 6 months later, it's moving in the opposite direction on the other side of the sun. So there's no way it could have zero velocity with respect to the ether at all different times of year. They even tried it at different elevations, but they didn't detect any fringe shift. Okay. Now there were some theories because this was very puzzling. It seemed like there wasn't any ether, any medium for light to propagate in. And a theory known as ether dragging, where basically the Earth would sort of pull the ether along, almost like a ball dropped in like a glycerol will pull along some glycerol with it as it falls in a laminar flow. But ether dragging was proposed to explain why the Earth appeared not to be moving relative to the ether. But various arguments from astronomy involving the relative position of various stars refuted this argument fairly well. So the conclusion then at the end of the 19th century was that the ether, light's rest frame, appears not to exist. Okay, so that's very strange, and that opened the door for some new physics, which we'll start looking into in future lectures on relativity, where Einstein starts to reconceive notions of measurement and space intervals and time intervals. Okay, so thank you for your attention. I hope you've appreciated what the ether is and how the Michelson-Morley experiment showed that the ether did not exist through the lack of fringe shifts in its interference pattern, and why this is so counterintuitive, because most waves move in some sort of medium. Okay, thank you for your attention, and I'll see you in class.